Hello there, my name is David Cater. In this video we're going to learn about the quadrature power within a capacitive circuit in AC. So it's a really straightforward concept. The way a capacitor works, we force a whole bunch of electrons onto one of the plates and giving it a very strong negative charge. It's going to require an electromotive force to make that happen, and as a result we develop this very strong electric field inside that capacitor. Alright, and so when we do this, we also kind of observe the fact that like charges are going to repel. And so any electron on the other side of on the other plate is going to be repelled away, and what we'll be left with is basically an absence of charges, and therefore we'll have a positive charge on the other side. Now, a couple of things about the way that is going to be storing energy. We have built up a very strong electric field. And we are, much like loading up a spring, we've loaded a bunch of potential energy into that capacitor. We can take it out of the circuit and it'll stay in there fully charged, as the electrons will have nowhere to go. And if we were to then rehook that capacitor up to a device, something like a simple resistor, then the electrons on that capacitor from one plate would start to travel to the other plate, and they would equalize. Once the charge is equalized, the volt potential would be zero, no more current would flow in that circuit. So just to summarize, we can store it up with electrons, with charge. That creates an electric field, and then we can later release that electric field and that stored up energy and create an EMF and cause current to flow. And so we can store and release power, store and return power in a circuit with a capacitor, and therefore we don't really use up power. We don't dissipate watts with a capacitor. So this is all about quadrature power, which is also known as reactive power. All right. And the thing is, power in general is measured in watts, and that's the rate of doing work, so producing heat or mechanical motion, and that's the energy you don't get back into the circuit. But seeing as we can store and return this power, we don't measure this in watts, we measure this kind of power in VARs. Okay, so volt amp reactive, that's the thing that we're looking for in this circuit. Now, simply just storing up the power in the electric field and having it return is a straightforward process. But what's very interesting is the sine waves and the quadrature power graph when we take a look at the way it works. So I'll bring that up here. All right, so let's just do a quick review of the sine waves that we have here. All right, so when voltage is at zero at the cap, that means the capacitor isn't charged up, and electrons are flowing onto the plate rather quickly, so we have maximum current. We can see that follows through. When the voltage rises up to the top, then the current is going to drop off because the capacitor is fully charged at this point up in here. Okay, so once we're at max voltage, we are at minimum current, and we can see that follow through all the way through. Current is rising when the voltage is at zero and therefore not charged at all, so we're going to be charging up the capacitor. And when the voltage rises to max, again on the negative alternation here, then our current is going to drop to zero because the capacitor is completely charged. So it follows through the entire way like that, and you can see that current is leading voltage by 90 degrees. Current's at max when voltage is at minimum. All right, so very interesting circuit, a lot of reaction going on in this circuit. So the last thing we want to do is kind of compare this system to the quadrature power of this mechanism, this electric field storing and returning power to the system. So what that looks like is this. We're going to be focusing on voltage. And when the voltage rises to max on the capacitor, that is when we have stored the maximum amount of electrons on that plate in that circuit, given the properties, and we have built that electric field. Right, so when the voltage rises, the quadrature power is going to be storing energy, and when the voltage drops to zero, the plate has discharged and the quadrature power is going to be returning power. And so let's see what that looks like. Okay, so if we take a look, just like we had said, voltage is rising, and so therefore our quadrature power is storing. And this graph is maybe a little bit different to what you're used to seeing, but anytime the quadrature power is in the positive area here, we're storing power. And anytime the quadrature power is in the negative below the line, okay, we are returning power. So we're storing power as voltage is rising. We are returning power to the system as voltage is dropping, and the electric field is being converted into an EMF. Over here, voltage is rising in the negative alternation, and so once again we are building that electric field, and we have a storage of power. And then over here, voltage is, we can see from here, voltage in red, it's kind of hard, but voltage is dropping, and we have a return of power in that circuit, and it keeps going on like this. So what we see here though is in one full voltage alternation, which is here, comes up, down, and then ends here, we have 4 components of the quadrature power: storing and releasing, and there, henceforth we have quadrature power. All right, so that's kind of the idea. Storing up power in the electric field, and we're able to return that power back to us. And when we see the graphs, we try to make sense of the fact that current is leading by 90 degrees in the AC capacitive circuit, and the quadrature power is storing and returning power 4 times in total, 2 storages, 2 releases for every full cycle of the sine wave. All right, so I hope you enjoyed this video, and we'll see you in the next one.